Hello everyone! Today we will continue to study the Basic Knowledge module. In this lesson, we will learn linear time invariant system. There are 3 points: the definition, the identification method, and the main properties of linear time invariant system. First, let's take a look at the definition of linear system and nonlinear system. Linear system refers to a system with linear characteristics. Here, linear refers to uniformity, superposition, and uniformity is also called proportionality. Of course, zero input response and zero state response of a linear system are separable. In mathematics, uniformity refers to homogeneity. If Ft acts on a system, the output is Yt. When Kft acts on a system, its output is Kyt. Its superposition refers to if F1t produces Y1t, and if F2t produces Y2t, then F1t plus F2t produces output Y1t plus Y2t. In a system, if the system is represented by H, F1t enters system H and produces output Y1t. F2t enters system H and produces Y2t. When we do linear operation on its inputs, if A1F1t plus A2F2t enters such a system H, the output should be A1Y1t plus A2Y2t. This is called the superposition of a system. Well, how to differentiate a nonlinear system from a linear system? There is a principle: linear operation first, then system operation, is equal to system operation first and then linear operation. In other words, we first do linear operation on the input signal F1t and F2t of a system H. Here, the linear operation includes proportional operation and addition. After linear operation, we put the synthesized signal to the system H to get its output, as shown in Figure 1. Conversely, if the signal F1t and F2t are put to the system H, respectively, then we perform proportional operation and addition on their output, and then we can get the final output, as shown in Figure 2. If the output of Figure 1 is equal to that of Figure 2, then such a system is called a linear system. Otherwise, it is a nonlinear system. Here you should know that for the system, if it is linear, you should deal with its external stimulus and non-zero state separately. Let's take a look at time-varying system and time-invariant system. First, let's look at the definition. In zero initial state, if the output response and input signal stimulus of a system have nothing to do with the starting point of time of the system is called a time-invariant system. Otherwise, it is called a time-varying system. That is to say, for a time-invariant system, its output response does not change with the time when its input signal enters the system. Well, how to differentiate time-varying system from time-invariant system? From the circuit analysis, whether the parameter value of the component changes with time determines whether the system is time-varying or time-invariant. In general, the parameter of components of a time-invariant system does not change with time. From the equation, we can differentiate according to whether its coefficient changes with time. In general, for a time-invariant system, the coefficient of its equation is a constant. We can also differentiate the two from the input and output relationship. If ft enters system H, we can get output yt. If we delay ft for a certain time, we can get ft minus t0. Then we put ft minus t0 into the system. If it is a time-invariant system, its output must be yt minus t0. The waveform is shown as follows. Now there is a signal ft. After it enters the system, the output is yt. It is such a curve. When we delay the time of ft t0 units and put it into the system H, then we can find that for a time-invariant system, its output yt is also shifted by t0 units, and it has no change in shape. The identification method of time-varying system and time-invariant system is similar to that of linear system. Time shifted first, then entering the system equals to entering system first and then time shift. If the condition is met, it is a time-invariant system. In Figure 3, the input signal enters the system H, and then it is time shifted. Then we can get the output yt minus tau. In Figure 4, the signal is time shifted first, and then enters the system H. Then we get hft minus tau. If the output of Figure 3 and Figure 4 is the same, the system is a time-invariant system. Otherwise, it is a time-variant system. Let's look at some examples. The first example, determine whether the system corresponding to the following differential equation is a linear system. According to the definition of linear system, we can prove whether the system has uniformity and superposition or not. We can find that the system does not satisfy uniformity nor superposition, so the system is a nonlinear system. When solving this question, when we have determined that the system does not satisfy uniformity, we can prove that the system is nonlinear. Let's look at how to prove. Assume signal ft enters the system. The response is yt. The equation is like that. When aft enters the system, if the system is linear, it can be expressed as follows. The input becomes aft, the output becomes ayt. We can get formula 1. This is the result when we assume the system is a linear, and we first do linear operation, then system operation. If both ends of the given equation are multiplied by a, we can get formula 2. In fact, formula 2 expresses the operation process that we first do system operation, then linear operation. How to understand? The so-called system operation first refers to when the input signal f enters the system, the output it produces is yt. We can get the given expression. At this time, we do linear operation on the entire system. That is to say, the system is multiplied by a. In mathematics, the expression is true. Obviously, the results of Formula 1 and Formula 2 are not the same, so the assumption that the system is a linear system is not true. Therefore, the system does not satisfy uniformity. Next, let's prove its superposition. We assume there are two input signals f1t and f2t entering the system respectively. We can get Formula 3 and Formula 4. when F1t and F2t enters the system at the same time, and if the system is linear, there should be the following equation. After the synthesized signal F1t plus F2t enters the system, we can get output Y1t plus Y2t. This is formula 5. The calculation performed here are first linear operation and then system operation. If we plus formula 3 and formula 4, we can get the formula 6. The calculation performed here are system operation first and then linear operation. Obviously, formula 5 and formula 6 are also not same, so the system has no superposition. Let's look at another example. Determine whether the following two systems are time invariant systems. For the first system, the rule of system 1 is to do cosine calculation on the input signal, according to the rule of time shift first, and then system operation. If signal ft is time shifted by t0 units and enters system, we can get output y11t, as shown in formula 7. According to the rule of system operation first and then time shift, if ft enters the system and produces output cosine ft, then cosine ft is shifted by t0 units. We can get y12, as shown in formula 8. By comparison, it can be found that formula 7 and formula 8 are the same. So system 1 is the time invariant system. For the second system, the rule of system 2 is to multiply the input signal by cosine t. According to the rule of time shift first and then system operation, the signal ft is time shifted and enters the system to produce an output y21t, as shown in formula 9. According to the rule of system operation first and then time shift, ft enters the system to produce the output, and then it is time shifted by t0 units to get y22t, as shown in formula 10. By comparison, it is found that y21t is not equal to y22t. Obviously, system 2 is a time-varying system. Let's look at the third example. Determine whether the system yt equals t times ft is a linear time invariant system. First, let's determine whether it is a linear system. Here, we first do linear operation on the input signal, then put the synthesized signal into the system H to get its output expression 11. And we first put signal F1t and signal F2t into the system H, respectively. Then perform the corresponding linear operation to get the output expression 12. It can be found that expression 11 is equal to expression 12. That is to say, the system satisfies the condition that linear operation first and then entering system is equal to entering system first and then linear operation. So the system given is a linear system. Let's determine whether the system is time invariant. First, put the signal ft to the system H to produce an output. Then time shift the output to get its final output expression 13. Then time shift the signal first and then put it into the system H to get the output 14. Obviously, expression 13 is not equal to expression 14. That is to say, the result of algorithm of time shifted first and then entering system is not equal to that of entering system first and then time shift. So this system is a time-varying system. Therefore, the system given is a linear time-varying system. Finally, let's look at differentiation and integration of linear time-invariant system. If a signal ft enters a system, the output is yt. When we perform differential operation on its input signal ft, and then we put the result to the system, we can find that the output of the system also does differential operation. Of course, if we integrate the signal ft, then put the result to the system, you can also find the output of the system also does integral operation. It can be proved by the linear property. Such differentiation and integration can be extended to higher order. Finally, let's make a summary. For a linear time invariant system, it has proportionality, additivity, differentiation of input and output, integrity of input and output. Of course, it also has separability of zero input response and zero state response. These are all we learned today. This class is over. Thanks for your attention. Goodbye.